Welcome everyone to TechDaily.ai. This deep dive is sponsored by Stonefly, your trusted solution provider and advisor in enterprise storage, backup disaster recovery, hyper-converged VMware, Hyper-V, Proxmox cluster, AI servers, SE365, a turnkey security appliance, public and private cloud. Check out stonefly.com for more info. Okay, let's get into this. Our mission today, is looking at something that sounds kind of ridiculous, honestly. Can you actually cool the working computer, specifically the CPU, using just plain old ice cubes, frozen water? We're really going to dig into the whole engineering journey here.
It does sound like a joke, doesn't it? But the basic physics, it's actually pretty solid. The initial idea, well, it works right away. Like the second ice touches the IHS.
Like a copper plate on the CPU.
Exactly. The integrated heat spreader, it just melts almost instantly, even if the computer's just idling, you know?
Wow, instantly. That's the key then, the speed. Why so fast?
Well, it comes down to the copper IHS itself. It has incredibly high thermal conductivity. That's its job, right? Pull heat away fast. So the fact that it melts the ice that quickly just shows you, bang, you've got immediate, really effective heat transfer happening. The ice is working right away.
Fantastic. Okay, so step one,
Yeah.
ice works, great, but now we've got water. Liquid water.
Exactly. And that's the classic PC builder's nightmare, isn't it?
Yeah.
Water, especially tap water or melted ice. It's got minerals, particles, stuff that conducts electricity. So yeah, water plus a running computer, that's a recipe for disaster.
Right, so the first big hurdle isn't even the cooling performance, it's just dealing with the water.
Yeah.
Instead of, trying to waterproof the whole motherboard, which sounds insane.
Yeah, complicated, messy.
The solution they landed on was way simpler, just containment.
Containment. Using, believe it or not, a basic metal measuring cup. You just place the cup right onto the CPU's IHS.
Okay, but you need good contact, right?
Absolutely crucial. So you put thermal paste underneath the cup, same way you would for any heatsink. That fills the tiny gaps, ensures the heat goes straight from the CPU into that metal cup.
And what happened then with this, super basic cup setup?
Temps dropped. Visibly. Like you could see it on the monitor. It worked. The cup pulled the heat. The water stayed inside the cup. Simple.
What did?
But yeah, it's not sustainable, is it? You can only fit so much ice in a measuring cup. Once that melts, the water gets warm, and the CPU temps just start climbing right back up. Doesn't matter how much ice you crammed in there initially, it becomes like a very temporary fix, not really a cooler.
Right, so we've proved if it can cool, but now the question shifts. Can we keep it cool continuously?
Yeah.
Which brings us to phase two, making this sustainable. And this needed some, creative thinking.
Yeah, the goal became, how do we feed ice continuously? Like an ice dispenser for your CPU.
Yeah.
Think of like a Pez dispenser. Or maybe those old napkin holders in diners where the next one is always ready.
Huh. A Pez dispenser for ice cubes. I love it. And the first attempt was literally a paper towel tube. Seriously.
Seriously, low-tech prototyping at its finest. Just cut a tube in half, taped it to the metal cup, stacked the ice cubes vertically inside.
Oh.
Obviously, cardboard plus melting ice, not a long-term plan.
Not ideal, no.
But it proved the concept. Queuing worked.
Okay, but what about performance? Going from a cup full of ice, lots of surface area, to just, one or two cubes at the bottom of the tube?
Good question. Temps were a little higher initially, yeah, because you had less cold surface actually touching the hot cup base. But, and this was the key insight, the cubes above the bottom ones, they stayed colder for way longer. They were insulated by each other. So even though the temps were slightly up, it lasted much, much longer. It offered real sustainability if you could just keep adding cubes to the top.
Okay, so proof of concept successful. Time to ditch the soggy cardboard. What came next?
Oh.
The more robust version.
Right. They moved to a much bigger tube, made of vinyl this time. And crucially, they used an epoxy compound to properly seal it to the metal cup. Now you've got a sturdy, waterproof chamber.
Makes sense.
And there was this unexpected side benefit. With a taller tube, you could stack more ice. All that weight, all those cubes pressing down, it actually created pressure.
Oh, interesting.
Yeah, that downward pressure helped make sure the bottom ice cube was always pressed firmly against the metal cup. Better contact, better heat transfer, just from the weight.
That's actually pretty clever, using the weight for better contact, passive engineering. But okay, you solve containment, you solve the feed, and physics throws another curveball at you. Buoyancy.
Exactly. The waterproof seal was maybe too good. The melted water had nowhere to go, so it stayed in the tube. And what does ice do in water?
It floats.
It floats, because it's less dense. So the remaining ice cubes started floating up away from the hot metal base of the cup.
So they're not touching the part that needs cooling anymore. What's in between?
Just the water. The melted water. And water, while it conducts heat okay, isn't nearly as good as direct contact with ice. It essentially becomes an insulating layer. Temps didn't immediately skyrocket, but the whole process got super inefficient. The ice had to cool the water first, and then the water could cool the cup, which cooled the CPU. You lost that direct, fast cooling.
Okay, so the melted water is now the problem. If it's the problem, get rid of it. What was the fix? The drainage idea.
Elegant solution, really. Drill a small hole, maybe quarter-inch, near the bottom of the vinyl tube, slot in a smaller tube, seal it up again with that same epoxy, point the little tube downwards.
And let gravity do the work.
Gravity drain. Simple as that. As the ice melts, the water level rises just enough to hit the drain hole, and out it goes. This keeps the water level low, so the stack of ice always rests directly on the hot metal plate.
Yeah.
Maximum contact, maximum efficiency.
Okay, so this is the fully evolved system.
Yeah.
The gravity draining ice tower. How did it actually perform under load? Like, what CPU were they testing? What were they doing?
They used a modern processor, but importantly, they ran it using its integrated graphics. That's actually a pretty tough test because the iGPU is on the same die, shares the heat spreader, and pumps out a lot of steady heat when you're, say, gaming on it.
Right, puts a constant load on it.
Exactly. So they were gaming, running benchmarks, really pushing the chip, and the temperatures, incredibly stable.
Just stable-like. What numbers are we talking?
It maxed out under load at just 40 degrees Celsius.
40 C. Wait, seriously, 40? That's really low. Just to give you some context, like a decent air cooler might let a CPU hit 65, 75 C under load. A good AIO liquid cooler maybe gets you into the 50s.
Yeah.
40 degrees, sustained using ice cubes in a tube. That's kind of staggering.
It really is. It just proves how much raw cooling power ice actually has.
Right.
And that drainage system was the key. It let the ice do its job efficiently, continuously. Huge success.
Okay, and how long could it sustain that? How long did a full tube of ice last before you had to, run back to the freezer?
Well, they ran one benchmark test for about 3 hours straight. Started around 4 p.m., finished just after 7 p.m. And the whole time, CPU temp, rock solid. Never spiked, never ramped up, just stayed cool until the ice was almost gone.
3 hours straight.
Yeah. So based on that, the estimate is you could probably get somewhere between, say, 2.5, maybe up to 5 hours of heavy use from one full tube. Depends on the room temp, the specific chip, that kind of thing.
Okay, so we did it. We got the answer. Yes, you absolutely can cool a computer effectively with ice cubes, sustaining really impressive temps, like 40 C for hours at a time. And all it took was basically a cup, a tube, some epoxy, and clever drainage.
That's the technical reality, yes, absolutely possible. But then comes the so what question. Is it practical?
Ah, right. The practicality.
And realistically, probably not, right?
Yeah.
We have fans, we have amazing air coolers, we have these sophisticated AIO liquid coolers. This ice system works, but it introduces this constant chore. You have to keep making ice, keep refilling the tube. It's manual labor for your PC cooling.
Okay, fair. It's not practical, like an off-the-shelf AIO is practical. But maybe practical isn't the only lens here. I mean, isn't the point of a deep dive like this sometimes just to see what's possible, even if it's unconventional? To push the boundaries.
That's a good point. From a pure, can we engineer this perspective, it's pretty brilliant. Simple materials solving a complex problem. But from a user perspective, yeah, it's a commitment.
But maybe the commitment is the interesting part. Think about it. In our world where everything digital feels infinite, on demand, this ice cooler, it introduces a visible timer on your computer use.
Huh. Hadn't thought of it quite like that.
We try to limit screen time with willpower, maybe software timers that are easy to ignore. But here, you look over, you see the ice level dropping. That's your time, physically melting away.
That is a really compelling visual. It completely changes how you think about the resource you're using the cooling.
Imagine trying to manage your productivity or your gaming time, not by the clock, but by the ice level. You don't say, I'll stop in an hour. You say, okay, I've got 2 stacks of cubes left. What's the most important thing I can do with that? The limitation is imposed by physics, not just your own discipline. It forces you to prioritize.
You'd have to be really intentional. Are you going to burn through that precious ice just scrolling social media? Or save it for the demanding work, the game you really want to play, the video render? The scarcity is real, tangible. That's actually fascinating.
A cool thought exercise, right? But, okay, let's bring it back down to earth for a second. There's still one big physical hurdle for the average PC build orientation.
Yeah. The reality check. Most PCs are towers. Motherboards stand vertically. Sticking a tall, potentially top-heavy ice tower sideways out of the CPU socket, probably not going to end well. Unstable, impractical in that setup.
So if the CPU isn't the perfect candidate in a standard case, where else could you apply this kind of super effective gravity-fed ice cooling?
Well, if you want the most heat in a typical gaming PC, you look at the GPU, right, the graphics card. Those things get incredibly hot, way hotter, often, and more concentrated heat than the CPU. They need huge cooling solutions already. And the actual processor chip on the GPU, it's usually accessible if you take off the big plastic shroud and fans.
Okay, but what about the orientation problem? GPUs usually slot in vertically too.
They do, but think about how they sit. In a standard case, the GPU processor, the actual chip, is usually facing down. But what if you just took your whole PC case and flipped it upside down?
Oh, so the GPU processor is now facing straight up.
Exactly. A nice, flat, horizontal surface pointing skyward. Perfect platform to mount our gravity-draining ice tower.
The upside-down PC with an ice-cooled GPU, now that's taking it to the next level, scaling the concept to where the heat problem is often biggest. Wow. This whole journey started with such a basic, almost silly question, and ended up tackling some real physics challenges with, like, plumbing supplies.
It really did. From just a cup to figuring out the feed, then beating buoyancy with a simple drain hole. And the result? A system that holds a CPU at 40°C under load for hours. It's a great reminder that sometimes the best engineering is about simplifying, not adding complexity.
So the big takeaway for you listening, sometimes the simplest ideas tackled one problem at a time can lead to surprisingly effective results. The answer to can ice cool a computer is definitively yes. But let's leave you with this final thought, moving beyond just the tech specs. If your access to technology wasn't limited by data caps or battery life, but by a visible, physical melting resource like ice, how would that constraint change how you value your digital time, how you interact with your devices? Would it force a different kind of efficiency, a different kind of mindfulness? Something to ponder next time you're reaching into the freezer. We'll catch you on the next deep dive.